Hello, statistical scholars. Today I'm going to introduce you to the notion of what a confidence interval is. So the interesting thing about confidence intervals and hypothesis testing, which are our next two big topics, is that they're very much related to the sampling distribution. And it's also the first time you're experiencing a new branch of statistics, the last branch we're going to talk about. So the first part of this class up until now was all about what we call descriptive statistics, or using whatever you have data-wise to describe what you're seeing and how I can summarize information that's before me. So the next step we're going to take is what's called inferential statistics, and that's the second branch we're looking at. There are other ideas too out there in stats land, but these are the two biggies that get covered in stats 1. So inferential statistics is we want to make conclusions about a population, but we don't necessarily want to do a census because that will take up too much time or too much money. It's usually just generally hard to be able to guess what a population is doing. So we have this population out here and it's got some parameter we're interested in, but it's not necessarily easy to directly come up with that parameter. So instead what we do is we sample, and we sample well. So this was the chapter 8 material on how to sample well, so you don't have bias, hopefully, and your sample represents the population well. And then you'll have some data that you gather from that well-drawn sample, and then from that you will gain a statistic. And then what we want to do is we want to use that statistic to estimate or infer what the parameter is going to look like. And that's what confidence intervals are all about. I have some data that I gathered from a sample from a population. I want to ask myself, what about that statistics that I gather from that data can I use to say things about the parameter, or how can I say things about the parameter using the sample? And it's all about estimating and confidence. All right. So I'm going to take you through this note sheet from our lovely Blackboard site. If you haven't downloaded this, you might want to watch along with this video. And I'm going to show you some, simulations along with this. So first we're going to proceed with looking at what a confidence interval is, but in order to do that we need to understand a couple things. So one of the things we saw previously is that we had the 68, 95, 99.7 rule that helped us determine how much data fell within so many standard deviations of the mean. So other ways you can approach that is you can also do 90%. So this would be like using that middle option from Minitab to pick out probabilities. So when you look at this first graphic, really what I'm doing is the middle 90%, and that corresponds with the z-score 1.645. So you get two of them, the positive one and the negative one, and this is because the distribution is symmetric. Now, we can also say that, oh, well, if we want to know where 95% of our data lies closest to the mean, or 95 middle away from center, I'm about 1.96 standard deviations away from the mean. Remember, z-scores are a number of standard deviations away from the mean. So depending on what your interval looks like, or sorry, not your interval, what your distribution looks like, you're going to be looking at so many standard deviations away or not. Okay, so for 99%, you get about 2.576. Now these are three very, very common z-scores with common middle values or common levels near the center of the distribution that we might want. So what we actually call these are critical values. So they represent the 90% around the center, 95%, 99% around the center. So the percentages around the mean, we call these confidence levels, or how confident you are you're within your data falls within 90% of the mean. So we'll start by estimating our population mean and assuming that the population standard deviation is known. Now, this is not always the case, so it's important to be aware of the fact that, when we're looking at a estimator, or we're trying to estimate something, we might not know parameters, so we might not know the population standard deviation. We might only have statistics, so there's some error introduced there, but we're going to pretend we do for now. So the first thing we're going to notice is that we're going to obtain a simple random sample, and that'll have a sample mean to it, and then we say that our sample mean is our best guess for what the true population proportion is. This is called a point estimate. It's called using a single value to estimate what's going on. Point estimates are usually not the best form of estimation because it's not necessarily true that the sample is going to match the population. You did the best you could, you drew a good sample, but it might not be equal. So when you're in future, you're asked to find a point estimate for the population mean, you're just calculating the sample mean. It's a single estimator. So let's look at an example. The pulse rates of 40 randomly selected women were recorded in beats per minute. The mean pulse rate from the sample was 76.3 beats per minute. Assume that your standard deviation is known to be 12.5 beats per minute. We'll need this assumption a little bit later. Here the value of our sample is 76.3, and our best guess for the population mean is the best guess, for our population mean. So we see that 76.3 beats per minute is our point estimate for the pulse of all women. However, what do you think would happen if you collect multiple different samples? Do you think you'd actually all get them all to be the same and all have that sample mean of 76.3? There's some sample variation in there. Quite clearly, you will not always get the exact same value for different samples. So this is where the sampling distribution is going to come in. So there's no variation from sample to sample. This is called sampling error. So the sample mean pulse rate would most likely be different than the previous sample mean. Scrolly, scrolly, scrolly. I bet you that's not dizzying to watch. Instead of relying on a single value to estimate the population, what we're going to do is we're going to do interval estimates. This is where the idea of a confidence interval is going to come along. So this estimate consists of two numerical values, a defining range of values, and a specific degree of confidence most likely to include it in the parameter of the estimate. And this interval of estimate is known as the confidence interval. So we create confidence intervals using different confidence levels. Most common are 90, 95, and 99%. I've seen 98%. I've even seen some biology papers that insist on using 80% in order to make sure that they account for what they think they can capture reliably, which you should be highly suspicious of 80% if you ever come across something like that. Anyway, so for example, what if we wanted to do a 95% confidence interval for the mean pulse rate? We would actually come up with 72.43 to 80.71 beats per minute. So we could also express this as my mean, or the average pulse rate for women, is less than or equal to, greater than or equal to 72.4 and less than or equal to 80.17 beats per minute. So the idea is that we're going to think about this as I'm adding or subtracting standard deviations. I'm going so far out in these percentages, just like we saw with these graphs, to be able to pick up a range of values. So we can correctly interpret this as a statement about the average. So if we want to select many different random samples of 40 women for the population whose mean pulse rate is mu and unknown, we construct a confidence interval for each sample, and it's approximately 95% of all confidence intervals will contain that true population parameter mu. Not all of them will. An incorrect interpretation of this is we would say that there's a 95% probability that we have mu. This interpretation is correct because, the interval either has it or it doesn't. There's no probability involved there. And you can't weight the probability on that either. You can't know ahead of time. You can only be confident that it is there or not. Anyway, so for the above example, our 95% confidence interval tells us that we will be using will result in an interval for the population mean of pulse rates 95% of the time. So 95% of the time, it's going to be there. That is, we came up with this interval using the method that gives us the correct result 95% of the time. It does not tell us that there's a 95% probability that mu lies between 72.48 and 80.1 beats per minute. So let me show you a little example of this. Let me make this a little bit, oh no, didn't want to do that. I'm going to make this one bigger. Okay, fine. Me pants. This one. Okay. So this is a confidence interval for the mean. This is my original sample that we're drawing off of. And then if you just, generate one sample, there's where it landed. And this gets really weird really quickly. This was not the simulation I wanted. Get ready to watch me pause this again. Sorry about that, I had the wrong one open. Good times. Okay, so if you want to see this in Spanish, you can too, which is kind of fun. So I'm gonna zoom this in. So the idea is that when I generate a confidence interval, I won't necessarily know the true proportion. So this is me generating some random garbage, but the point is that I'm simulating some population proportions here. Where's the one for the mean? Whatever, this will work. So the idea is that here, p hat, this is the wrong one. I don't want proportions, I want means. There we go. Okay, so here's what I'm dealing with. I've got some mean that I'm going to draw, and I'm going to change this to being something more, screw it, I'll leave it at 0.5. So my population mean is 0.5, my population standard deviation is 10, my sample is 100. So the idea is that I'm going to draw a sample randomly, and it's going to calculate a confidence interval about that. So watch what happens here. Whee! Okay, so it drew a bunch of samples and it makes this little dot, and there's all kinds of stuff going on here. So it drew this sample of 100 individuals from my population that looks like this. And it has the following mean and the following standard deviation, which is slightly different from the original population, worth noting. All right, and then you plot that down here. So what I've got over here is the more interesting graphic. So there's this straight line where a 0.5 is. That's where the actual true mean is. And then here I've got a dot. That's what my sample mean was, that negative 0.0017. Notice this is just shy of 0. And then this green line here is the interval of all possible values that were made up from our confidence interval. Yay! So if you notice, this is the green line actually capturing the true proportion, that 0.05. So I'm going to redo this again, but I'm going to do, like, instead of just one sample, I'm going to do 50 samples. Bonk. Oh no! Look at that. There's 50 of them, and I'm 95% confident, and 1, 2, 3, 4, 5 of them failed to capture the true population proportion. So you see how there's some variation between where these land and how wide they are? And occasionally you'll get a sample that when you do the 95% confidence interval, it fails to capture the actual true mean. This is called an error. You'll talk more about those in Stat 2. You don't really get a chance to talk about them in Stat 1, unfortunately. So down here we have a blocking of all of our sample means and how often, so for instance these red dots over here and these red dots over here, blocks rather, are the ones that came up and failed to capture our population mean. So 1, 2, 3, 4, 5 out of 50, that's not very good, seem to have failed to have done the job. I'm hoping this helps you picture what's going on here a little bit better. Alright, and I hope you don't hear the music going on from the class next to me. Anyway, so how do you create a confidence interval? Well, you'll begin by creating, something that goes 95% away in either direction. So the shape of the distribution for the sample means will be normal, provided you have something large enough. So sample size larger than 30. We're going to see what to do and what happens if you're not big enough. We want the mean of the sampling distribution will be the same as the population mean, which will be, unfortunately, the sample mean for us because we won't know the difference. And then the standard deviation is equal to the standard deviation of the population divided by the square root of the sample size. Yay! This is going along with the sampling distribution stuff from last time. So I'm looking on the sampling distribution, not the original distribution, because I'm doing samples. Over here my sample size was 100. Clearly this is going to be very normal looking because it's bigger than 30. Anyway, so since y bar is normally distributed, notice the bar, not the just regular y, because we're talking about means of means here. With the 95% of all samples will lie within 1.96 standard deviations away from the mean, 2.5 in each tail. And we know the standard deviation for the sampling distribution, which tells us, how far away we're going to go in each direction. So again, number of standard deviations away from the mean, how large the standard deviation is. So I'm moving 1.96 standard deviations in each direction. So I'm moving away from y bar by this many standard deviations and moving away in the other direction by this many standard deviations. So I'm both adding and subtracting in each direction to create these bands that we see. Anyway, so and using some algebra, you can quickly see that this inequality will capture the mean. So be thinking back to this idea. Anyway, so we can express the 95% confidence interval for the population mean as y bar plus or minus the 1.96 times the standard deviation. So this is that critical value showing up again from the 95% confidence level. So this value is going to change based on how confident you are. So if you're 90%, you'd be using, I forgot what that value is because I never use a 90% one. I always end up using 95. Who knew? It's 1.6 something. Oh, who teaches this class? Anyway, in general, a confidence interval for a population may be expressed as the following. So y plus or minus the how many standard deviations away times the how wide are my standard deviations. So it's just moving you standard deviations away. This is called the margin of error, or how spread or change or how far you go in each direction for the confidence interval. So when you're looking at margin of error, or if you're listening to polling numbers, if you're watching, recent election coverage or any election coverage, they always report their margin of error or how far off they expect to be in either direction. That's what they were talking about, how wide their intervals were. Yeah? How far you go in each direction, or the length of one side of the interval. Anyway, let me pull up that graphic really quick. Oh, Word, don't fail me now. Anyway. Oh, fine. Evil beast. Anyway. So if you look at this document, if you're thinking about the margin of error, really it's all about how far I've gone from the mean. So there's my center mean, and then I add one standard deviation, or times the number of standard deviations, how wide they are, to that mean in each direction. So your margin of error is sort of the width of the interval, but not really. The entire length across would be from here to here, which is 2 margins of error, because you're going one direction for plus, one direction for minus. So when you look at your y bars, when you subtract your standard deviation from the mean and you add your standard deviation from the mean, you sometimes catch mu, sometimes you don't. So this is a larger version of the graphic we have down here. Okay. So in general, when you're constructing the standard deviation or the confidence interval, for a mean, what we want to do is we want to sample from the population and verify the following requirements. If you don't verify these, you can't really use the sampling distribution, and therefore you can't really create a confidence interval. So that you've got a simple random sample, and either the sample population is normally distributed, or the sample is large enough to where it's going to look normally distributed, because we're using the sampling distribution. So if you calculate the sample mean y bar, then you find the critical value based on what confidence level you want. Then you calculate your margin of error, which is just the standard deviation times the confidence level, and then you'll add and subtract that from your mean to create the upper and lower confidence limit. So the subtraction will create the lower, the addition will create the upper. In general, whenever we write intervals, we always write the smaller value here and the larger value here. If you're not sure which is going to come out as which, calculate them both and then place them. This is exactly what Minitab does as well. So if you're wondering how it's going to place them, there you go. So now we create a 95% confidence interval for the mean, for the pulse rates of females who are having their hearts looked at, sometimes in Heartland. That was bad. I apologize. Okay, so what we would do is we would first calculate the mean, which we found using our sample data. It's 7.63. Then we know the standard deviation to be 12.5. This was given in the problem. Occasionally this won't be given to you, and then we're going to need to get into some other issues, but we'll get into that in a minute. And since our sample size is 40, we know that this is definitely going to create a approximately normal central words. The sampling distribution will be approximately normal thanks to the central limit theorem. Oof. That was hard. All right, and then we calculate the margin of error. So we take that confidence level, Z star, we just found, our critical value times our standard deviation divided by sample size. There's that calculation, and we come out with 3.874. We will add and subtract that to our mean, which is what we're doing right here to create our confidence interval, and we get the upper and the lower, and there we go. So we would say that the population mean pulse rate for women is 76.3 plus or minus 3.9 beats per minute, and the 95% confidence level. Now, this looks like numerical garbage. That's not very natural. I usually write my interpretation of confidence intervals like the following. That one is very technical. Here's a more natural sounding one. We are 95, ooh, I forgot my quotations. Percent confident that the mean pulse rate, my typing's great today, for women is between 72.43 and 80.17 beats per minute. It's just a little more natural sounding. So if you like that one, good on ya. It'll be a good time. I'm going to save this and then overwrite the file that you look at for this so you'll see that. Good times. Okay, so if we only wanted to be 90% confident, what would change? So you go back looking in here, you're like, where's confidence? Where did I use it? I needed, what, it was up here? No, where did I use it? Right here, calculating our z star, our critical number. So that's what would change. And since this is going to be a smaller value, 1.645, therefore my margin of error is going to be smaller, so my interval is going to be smaller. It will be narrower. That's what's going to happen here. Okay, so here's how you do this in Minitab. So we go up to Stat, Basic Statistics. There's two you're going to use a lot in here, the ones at one sample Z, the one sample T also will be used, and then the one proportion. I said two, there's three. And then the one proportion test. We're going to do a one sample Z. And now this looks a little weird, right? You're like, oh my god, these pictures don't match. But wait, there's more. Check this first drop line. I always check this first. If your data is in here, this is the one you're going to choose, one sample in each column. We have summarized data though. We have data that was given to us in a problem. So make sure you double check that arrow drop down. We want summarized data. So we put in our sample size first, and then our mean. It's my decimal. Jeez. And we know our standard deviation. And then we're going to hit options. And notice there's our confidence level. We never really change the alternative hypothesis unless we're doing a hypothesis test. Don't worry about that for now. I'm going to change this. Well, it's 95 over 95. Okay, here we go. Ta-da! Yay! Okay, so this produces a lot for you. It gives you the mean, standard error for the mean, fun times, and then right here is the confidence interval, which I highlighted in red on your note sheet. And you can also find the margin of error using this if you want to by just taking the difference of your upper interval minus your mean, because remember this is the mean plus the margin of error. So if you subtract the mean, then you end up with, you know, the margin of error. Anyway, we can also calculate sample size if we have a particular error in mind. Whoa, what do you mean by that? Well, let me show you. So if you take the margin of error equation, you notice that it has sample size in it, and you can actually calculate or rearrange this using algebra to solve for n. If you do that, you get the following equation, and then you can calculate sample size. One thing that's a word of warning, I wrote this in red and bold letters, we always round up with this. Because if you want a margin of error of 3% and you come out with like 600.3 people, you can't have 0.3 people. And if you choose 599, it will be smaller than 3%. If you choose 601 people, you'll be, oh, sorry, not 599, 600. If you choose 601 people, you'll have more than enough. So we always round up with sample size, even if it's close and like you're naturally told not to. Anyway, Minitab will not do this for you, so you, that one, know it. Or know this one and how to solve things. Good times. Anyway. All right. Let's talk about what happens if I don't know sigma. Oh my god. Well, it turns out if you don't know sigma, you need a different sampling distribution. Poop. It's called the student t distribution because it was named after one of the Guinness researchers known as, well, his first name was Student. That's where that comes from, if you were wondering. Anyway, so he was working with relatively small samples, because if he chose large samples from the Guinness beer, they'd have no beer for them to be able to sell when they were trying to, you know, do things. He was actually trying to measure alcohol levels to make sure that each batch was relatively the same. And he came up with this distribution using his multitudes of data from beer. See, beer doesn't always do bad things, I guess. I don't know what to say about this. Anyway, it's a really interesting example of statistics. I'll see if I can find a nice historical article on it that's pretty easy to read and not horrible, because a lot of the ones I've read are horrible, but you guys can take a look at. Anyway, so because you know sigma, and because typically you don't really know what the population looks like. Remember back to that picture, population blob, not really sure what's going on. You need a different distribution. So one of the things that's interesting about the student t distribution is it looks a lot like the normal distribution under certain conditions. So it's symmetric, it's unimodal, it's more spread out than a standard normal distribution, which means it has longer tails if you're trying to picture this. And as the sample size gets larger, the student-teacher distribution looks more and more closer to normal. In fact, when it's bigger than 30 in sample size, you start to look very, very normal, which is why we use that bigger than 30 one for when we decide whether or not we're going to use normal. Anyway, so when you're calculating a confidence interval with an unknown standard deviation population standard deviation, sigma, if it's a simple random sample and either the sample is from normally distributed population or it's a large sample, that's one. If you don't, then we're using t. It's not that different. So when this is the case, we're going to be using the sample standard deviation. So we're going to be using little s, not sigma. Anyway, and then we're going to, this is going to create some unreliability because we're going to be using the sample instead of the population. So there's a new error introduced into this. This is often called the standard error for this reason, because you're using samples over population parameters. Anyway, and therefore, we're going to end up using a wider interval to make sure we're a little more reliable, and our critical values are going to come off the t distribution, and hence they will be called t star. And there is a t table if you would like. Yeah, t table. Fun times. Although I'm not going to use a t table here, I'm going to use Minitab to do all these calculations because it'll do them. Fun facts. Anyway, so let's say we're looking at a sample of size 32 and a randomly selected normally distributed population. Find the critical value t star for the corresponding 95% confidence. Here we go. So our degrees of freedom is 22 here. We're going to go up to Minitab. We're going to go to graph. I like probability distribution plot for this guy. Probability view, because that's the one we always use. And then I'm going to change this. We're no longer on the normal. We're going to use D. My degrees of freedom is 22. And I'm going to go to shaded area and choose middle. And so since I want 95% in the middle, I have 5% in each tail. Oh, sorry, 5% in the tails together, which is 2.5% if you divide it in half equally. Here we go. Ready? Ta-da! This looks pretty normal, right? 22 is pretty close to 30. Let me do another one, just for funsies, with a much smaller degree of freedom. So you can see how this guy looks. So I'm going to choose something much smaller, like 2. Here we go. Oh no, that looks very unnormal. Oh, it looks very tiny in the middle and kind of tight and weird and like a hat kind of. And then it gets really longer in the tail distribution. So notice it also gives us a different T. So degrees of freedom, very essential in here. Be careful. If you're wondering, why is the degrees of freedom one less smaller? Because when you're calculating with the t distribution, more often than not, you're including the sample mean. So you've got one value in there that gets measured twice, so we subtract one. It's a little interesting. Anyway, so when you're dealing with a confidence interval for our mean, and you don't know these population's standard deviation, we're going to be using the t distribution, so our margin of error changes, but our estimation stays the same. Confidence intervals always look the same. Some sort of estimator plus or minus a margin of error. That guy. And then how we calculate the margin of error varies based on what kind of estimator we're attempting to do this with. So that's about it. Let's go ahead and do one using Minitab. So let's look at the following example. A sample of 123 people, age 18 to 22, reported that the number of hours they spent on the internet on average per week. The sample mean was 8.2 hours, and the sample standard deviation was 9.84 hours. Assume that this simple random sample from the population aged 18 to 22 in the U.S. construct a 95% confidence interval for the mean population number of hours per week on the internet for people aged 18 to 22. Whew, mouthful. Yeah, I hope you guys don't enjoy it. I mean, listening to this is fun. So let's look at the solution. We're going to verify our requirements. Our sample is large. It's a simple random sample. It's approximately going to be normal, but since I don't know the population standard deviation, I'm going to be using S instead, and therefore I will be using the t distribution. Cool beans. Our degrees of freedom is 122, which is just me subtracting 1 from 123, and there's our margin of error if you find the t. And then we can calculate the confidence interval by hand by adding and subtracting that confidence interval, the 8.2 hours plus or minus the margin of error. Now, you can also do this on Minitab. Woohoo! So we go up to Stat, Basic Statistics, and you choose one sample T instead of Z. And here, once again, I got to change this to summarize data. My sample size, 132. It's going to use that to figure out my degrees of freedom. I'm going to put in my mean and the standard deviation of this sample. Let's go to options. Still 95%. We're good to go. Let's hit OK twice. Look at that. So if you compare that to the one you got above, it's a little more detailed. It's more decimal places. Fun times. There you go. So, what we would say is we're 95% confident the mean number of hours per week spent on the internet by people who are 18 to 22-year-olds is between 6.44 and 9.96 hours. Whoa. It's quite a bit. Anyway, I use the internet a lot, but I'm not in that age group. Weirdness. I want to see them do this for teachers. Bet you it's a lot. Bet you it's even more for people who teach online classes like me. Anyway, so quick little summary lowdown. Hey, if I don't know the population junk, or I have a small sample, it's tea time. Okay? You know. Be careful. Don't do red things. Let's look at how to do this for the population proportion. So quite similarly, when you're dealing with a proportion as your estimator or your parameter that you're looking at estimating, we use p-hat, and we use p-hat's distribution for doing this. So this is the thing I was accidentally pulling up earlier where I was like, hey, proportion. Nope, you can still do this for proportions as well. So if we look at a sample proportion, my p-hat is x over n, so x is number of successes and n is number of trials. So that's your sample proportion. You can actually use this as a point estimate for the true proportion. So in a Gallup poll conducted in 2004, a random sample of 1,004 adults resulted in 843 of the respondents saying that they were satisfied that things were going in their personal lives. There's some Thanksgiving conversation for you. A sample proportion of Americans who were satisfied is about 84%. So here the sample proportion p-hat is a point estimate or best guess for the trial population proportion p. So I got my hat and I'm trying to infer what's going on with my p. So we're at this step. I'm like, this is my hat. I think it does a good job for p, the parameter, maybe. Anyway. However, again, point estimate, not the best guess. It's a best guess. We don't know how confident we are in this. Let's do some confidence intervaling. So one of the interesting things on here is you need to be careful because, again, with p-hat, it's a little bit different requirements for the sampling distribution in order for things to work out best. So simple random sample still required. Independence or the 10% conditions. Remember, this can't be more than 10% of your population that you sampled off of. And you need to have the success-failure condition be true. So you need to have that your number of successes and number of failures should be greater than or equal to 10. If not, it's simply just too small to do this. Otherwise, you don't look normal when you look at the binomial distribution. Alrighty, so just like before I mentioned this, when you look at your estimator plus or minus the margin of error, so our estimator that we're using in this place is our p-hat value, and we're going to add or subtract our margin of error times. So when we calculate the margin of error, it's going to be our z-score times the standard deviation of the sampling distribution, which was p-hat times q-hat divided by n. So notice here I'm using the hats, which is a standard error, not a standard deviation. Uh-oh. Weird. Anyway, so in a Gallup, let's do an example. That was a bad lead-in. In a Gallup poll conducted in 2004, a random sample of 1,004 adults. I just read this one. I'm not doing it again. Let's find a 95% confidence interval for the estimate for the population proportion. First, we need to check that the requirements are satisfied. Is it a simple random sample? It's a poll. Oh no. So it might not be. Oh well. 10% condition, I'm pretty sure there's more than 1,004 adults in the Americas, so, or Americans, check. Number of successes, 843 versus 161. Yeah, we're good. Binomial can be approximated by a normal. Check, check. Let's do the 95% confidence level. So we check our z-score, that's at 1.69. There's certain ones that are very, very common. 1.69 is one of them. Let's calculate our margin of error. We have P and Q. Notice I'm not rounding here. I want to be more accurate in my estimates, so I'm not going to round these values. I'm going to use what I had. So P, Q divided by sample size, take the square root and multiply by our critical value. We get this as our margin of error. Now we add and subtract our margin of error from our P to calculate our upper and lower bounds. So there's our lower, there's our upper. So it's somewhere between 81.69 and 86.23%, which is exactly what we're going to say in here. The 95% confidence interval proportion of all American adults who are satisfied with the way things are going in their personal lives is between 91.7 and 81.7 and 86.2%. The confidence interval often reported as its estimated success rate is 84% with a margin of error plus or minus 2%. That's a little bit typical of what you're going to see for polling. Anyway, level of confidence should also be reported, but rarely is by the media. Anyway, so if you want to do this using Minitab, we go up to Stat, Basic Statistics, and here we're going to go down to one proportion. So the proportion tests are all together, the mean tests are all together, and they give you these little pictures. So mean with a Z, mean when I'm not sure what's going on, and then P for proportion. So these are the three we're going to be using a lot. And again, I don't want to use data, I want to use summarized data. So I put my number of events, this is your number of successes, and then number of trials. Let's go to options. Oh, crap. Well, if you look at the options, you get this. I forgot to hit normal approximation, sorry about that. So stat, proportion, options. I'm going to change this to normal approximation because then it's going to be more accurate to what your calculator is going to produce and to what MyStatLab is going to produce. So that's the one you want to use. Hit OK. Hit OK. These are slightly different, just so you're aware of that. And it's slightly more accurate than doing it by hand. Anyway, so you also can use the standard error or margin of error for a proportion to find sample size. So if I take this formula and solve for n, you will get the following. And again, always round up. If you don't know what P and Q are, or if you don't have a value for them, what you can do instead is use the worst case scenario, 0.5 and 0.5. If you'd like to see a video on how to do that, I'm also going to attach an example video that goes through why 0.5 and 0.5 for P and Q is the worst case scenario, and the answer is the quadratic equation, which weirdly shows up here. Fun facts of the day. And again, Minitab will not do that calculation for you. Sorry this was so long. I hope it's been informative and helpful. If you need more help, please don't be afraid to check out our YouTube channel, which has more examples in it than just this. Where is my pause? Ending awkward. Bye!